I'm willing to make a bet here now that probably all of you know exactly which web framework you're using at the moment in your current project. But I'm betting that not all of you remember which HTTP server you're using or what is the thread pool size in your HTTP server. And that's fine. I mean, I know it because I was there as well. Web frameworks are the things that we use daily, that we write daily, while HTTP servers, well, they just sit there somewhere in the basement doing the hard work. My name is Adam Dubiel, and for the next 40 minutes, I would like to talk about those things sitting in the basement doing all the heavy lifting, meaning HTTP servers. Because whether it's good or whether it's bad, they became a de facto standard, a fundament for most of the microservice deployments. But before I jump into the topic itself, why am I even here? So why would I want to talk about this kind of a, I don't know, maybe dull topic, like HTTP servers? I mean, who cares? They're not so shiny. So I work at Allegro, and if anybody's unfamiliar with this, we're the biggest e-commerce site business in Central Europe, and we have something like 12 million users, and we hire almost 600 engineers now, so it's 500 plus. And we've been doing microservices for quite a long time. So like before it was cool and before people started bashing it, which is quite, which is quite a way to do this year on the conferences. So currently we're running something around 400 microservices in production. But that's not something unique. A lot of people are using microservices at the moment. My role at Allegro is I'm the tech lead of Skylab team, which is doing a lot of internal tools. So we're kind of working in the middle layer. So there's the infrastructure on the bottom, us, Skylab team, and then there's business development. And our flagship product is Hermes, open source PubSub built on top of Kafka. But most importantly, we are taking care of our JVM starter, JVM stack. So this is the thing which every single JVM service in Allegro uses, which it builds upon. There's not a lot of code in there because we don't want to write code. It's all based on Spring Boot. What it gives you the basic connectivity with all of our ecosystem, but most importantly, it tries to prevent people from making the same mistakes. Meaning, we provide a lot of factories like for HTTP clients, factories for thread pools, to get all the stuff monitored, to provide sane defaults. We also provide HTTP server monitoring, and because of our role, because of us being the maintainers and developers of Andamio, we have to keep track of how the servers work and how to make people's life easier, and by this making Allegro more resilient and fault-proof. So these are, as I mentioned in the beginning, there are some things that we know perfectly about our HTTP stack, and those are the frameworks. So you could wake me up in the middle of the night and I would be able to write this kind of controller for you because, well, this is what I do daily. This is the code that I review daily. So I have this REST controller. I know all the newest idiomatic ways to write those things. You can see that I'm using the get mapping annotation instead of resource mapping because this is the new thing in Spring 4.3. Yes. And you could probably I could probably write something in Jersey as well. I haven't used it for a while, but I mean, it's easy, and I still remember that the annotations are a bit different, but it's all the same. And hell, after being to a few conference talks, even though I have never deployed a Spring Flux application yet, I could probably, just change some types and write a Flux controller as well. It's easy. I mean, these are the things that we all know really well and that we actually write daily. And this is the crossroads moment. So you can either take the blue pill and just stay in the controller world and, I'm writing REST things, so everything's fine. Or you can take the red pill And because you're all here, I assume that you're willing to take it and go down the rabbit hole. So the first hard truth after swallowing the pill is that our applications are mostly busy wasting resources. So this is what our applications actually do. So you probably know this comic strip, the programmer's excuse to not do anything, things are compiling. Well, our applications have the same kind of excuse. They're just waiting. They're doing nothing. They're waiting. And we're going to dig deeper into this because it's quite interesting. So let's say we have this important business service, because we're writing business things, and business things sound important, they are important. So there are layers to this kind of applications, and they're usually more or less the same. So we have some kind of an HTTP server, we have some JSON mapping thing going on, then we have this, holy business logic. Then we have some, Bison mapper, so a database, probably Mongo. Doesn't matter much. And as I would like to imagine, my application is doing really important business stuff. So if it's doing important business stuff, that means my CPUs are doing the important business logic. So this is what I would like to, this is the way I would like to perceive my app. Unfortunately, in most of the cases, the reality is really different. So let's just, rename the application. It's actually JSON to JSON mapper waiting service. So it's mapping JSONs and it's waiting. This is what our application do. And when it comes to at least when it comes from the CPU perspective. So while it might generate some value, from the CPU perspective, we're probably just waiting on stuff to happen. We're not doing anything. There's this green bar. You can see that it's really, really low. This is the place where some important magic happens, but all the other time, we're just waiting. And we can be waiting for a number of things. So we can be waiting for database query result. We can wait for HTTP calls from other service. Actually, any type of I/O interaction means we're going to be waiting. And the question is waiting so inherently bad? I mean, should we be ashamed of waiting? Well, we shouldn't if we do it with style. So if we have a proper style, well, we can wait, but we have to do it nicely. So I would like to go through the evolution of HTTP servers, of how they changed through the times in terms of waiting, looking from this perspective. And to do this, we're going to have this kind of a model application I'm going to use. And this is a very simple application. It just has two endpoints. One, the report. This is the important business logic. This is the things that all the people in our company are using. And there is a status. Status is totally unimportant from business perspective, but it's crucial for the application to work. So there is, maybe some load balancer or discovery mechanism using status to actually determine if the application is still on, if it's still alive. So we want it to be responsive. Back in the old days, there was something called blocking I/O. That was the thing that everybody was using. And the first application I was writing in Tomcat, they were using it as well. So let's take a closer look at what we've left behind. So the old school Tomcat application, what it would actually look like. We would have this kind of an acceptor threads. By default, it was just one thread. I'm going to explain what it does later on. And then we had all the big request processing threads pool. And it was like 200, 500, 1,000 threads. It depends on who actually configured it and if there were any problems on production. And because we have some kind of a thread pool, there's, of course, a queue. OK, so we have the acceptor threads and the request processing threads. What's the difference? Why do we have two types of threads? Well, the acceptor threads are actually responsible for maintaining the connections. So those gray lines, these are the connections. And they do nothing more. All they do is just keep track of connections. Whenever a request comes, it's immediately sent to the request processing threads. So acceptor thread does almost nothing. Everything happens in the request processing thread. And from perspective of one thread, this is called thread per request model. So We do the writes, we do the business logic, and we do the reads, all in the same thread. And write and read are the I/O operations, though, so we're going to probably get some blocking in there. But we're going to get to this later on. So let's imagine a situation in which there are a lot of users using our dash report endpoint. And the requests are just coming in. And just to make it easier, I only left the thread processing pool on the slide. So we have the thread processing pool, and people are waiting. The reports take a long time to finish. Yeah, it's the motorbike. It takes a lot of time to finish. And at some point, this thread pool is finite, actually. So we're going to run out of space. And this means our server becomes unresponsive. And while it wouldn't be, well, it's a disaster by itself, but it will be even more of a disaster when the status endpoint stops being responsive. Because while our users will just wait, because the report fails to finish, when the status becomes unresponsive, our application is marked as dead. There's no more traffic flowing to it anymore. It might be restarted if we're running in some containerized or managed environment. So our application is alive, but it's taking, it's dedicating all of its resources for the reports, but still it's marked as dead because it cannot respond to the simple status query. So this is a bad thing that could happen. It only adds to the mayhem of the incident. So we're already in a fire mode, in a firefighter mode. So we are fighting the fire on the production because the report is not responding. But then our application goes down from the load balancer, from discovery service, and it's just getting worse. So there's a simple remedy for this, which is called asynchronous I/O. And this is the thing that got introduced to the Java world with servlets 3.0 spec. And it all looks the same from the server side perspective, like the acceptor thread and so on, if we were using Tomcat. But the things get very different when you take a look at what a single thread can do. So it's no longer thread per request model. Now we can delegate, which means that we can escape from the request processing thread pool and delegate the work somewhere else. With Spring, it's easy. You can just put some async on it and everything should work. And this gives us an opportunity to actually protect the endpoints which need to be responsive, and it gives us and it protects us against the domino effect. So we have the report and endpoint, and everything that's actually happening in the request processing threads is delegating work to the other thread pool. So reports, even if there are a lot of them, they're just gonna choke the other thread pool, but our main thread pool, which is responsible for serving requests and responses for HTTP server, is going to stay responsive. This means that dash status is still responsive. Looks like a win to me. But so yeah, the one thing you need to watch out for is when you're using different thread local based mechanisms, and there are a lot of them in Spring, that you actually have to care about moving data from one thread pool to the other, because thread local, just thread context, you're moving to the other threads, so you have to take the information with you. But it's not ideal. It's some kind of a solution. It's good to have it, but it's not ideal. Why? Well, let's imagine we have some kind of a slow publisher, and as you've seen, the read and write things are still blocking. So if you have someone who's actually just dripping the data byte by byte, they're doing it fast enough but really, really slow, it can be that the request processing threads are actually busy waiting for the client who is dripping all this data in, because it takes a lot of time. And this is actually a base for the slow lorries denial distributed DDoS attack. Or you can just take a PHP server, put it under a heavy load, and it's going to behave the same. Yes, so it's just dripping the information. It makes all of your threads wait for the information to come instead of serving things. So async is a nice solution, but it's not enough. So then we have the other way, which is non-blocking and asynchronous. So what's the big deal with NIO? It's non-blocking I/O. How does it look like? So while in the previous model we had these acceptor threads, now they're called different, and they behave different. So we have the I/O threads. This is the first pool of threads. And then we have worker threads. But it's not only the change in names. Oh, of course, there's a queue. Whenever you have a thread pool, there's a queue. Important thing to remember. So we have the I/O threads. And what happens when the request comes in is that the I/O threads, thanks to their name, all they do or they care about is taking care of the I/O. So they do all the read and write operations, while all the other threads, all the other thread pools we might have in our application, they just do the work they were supposed to do. So everything with the I/O happens in the I/O threads. And they are smart. I mean, they are not like the threads we had before that were actually blocking on reading. They're actually, sharing the work, and they are just doing it in a non-blocking manner. So even if somebody drips 1 byte by 1 byte, it doesn't matter because I'm not waiting actively for him. I'm just reacting on the data that comes in. So if the byte comes in, I'm just going to put it somewhere. But if there's no more data from this client, I'm just going to, go and care for the other client. So I'm not blocking. I'm not waiting for someone. I'm just reacting to the changes. I'm just reacting because of the information I get from the system. To stay efficient, the NIO thread number is very close to the CPU core number, and it depends on the server. So, for example, in Undertow, the actual number of NIO threads is 2 times the CPUs. In Tomcat, I think it's matched with the CPU numbers. This came in Servlet 3.1 spec, so it's usable in our old school controllers like Spring MVC since Servlet 3.1. And if you want to, the poster boys for this kind of I/O, like non-blocking I/O, are of course Netty and Undertow. But it's also possible with Tomcat. And actually, the funny thing is that since Tomcat 8.5 and Tomcat 9, they totally got rid of the blocking I/O thing and put the NIO by default. And the NIO Tomcat connector is also the default if you're using Spring Boot with Tomcat. So your application behaves quite nicely, actually, even though it's Tomcat. And when you think of Tomcat, you don't think of nice things. You think of annoying things. So the question is, if we have so nice non-blocking I/O stuff, do we even need the worker pools? Why do we have the worker pools in our applications? Why do we allocate so much threads? Well, you remember this one. So we have the I/O threads and worker threads. And the different way to look at this is that we have the super fast I/O threads. They are really fast. They're really good. And then we have this, actually the anti-corruption layer, because the things that we use to communicate with the outside world are usually blocking. So the old school database client drivers, old school HTTP clients, this is the place where we are actually waiting. So our server is super fast, is not blocking, and then it throws the job over the wall to the other thread pool, and the thread pool does future.get. It just waits. It waits for the HTTP clients, for the database clients. So the worker thread pool acts as a kind of an anti-corruption layer, because the one thing you can't do, you should never do, is to block in the I/O thread. They are meant to be handling I/O. They are meant to be super fast. Never block there. If you block there, there's so little of them, your application is going to crash and burn really fast. So OK, there's also the other way to look at it. So we have the super fast Tesla. This is here. And then we have this old school, carriage on the other side. These are the drivers. But so is it impossible to actually write a nicely behaving application at this moment? Like, if you came back to work, is it impossible to write a nicely behaving application? Well, the sad thing is that it's actually possible, but there are a lot of things that we rely on that make it hard. Why is it so? So, once again, a different perspective. We have super fast NIO servers. We have this anti-corruption layer, and then we have the old school APIs, and then we have, once again, the super fast things. So, if you're using something like Apache async HTTP client, it's actually non-blocking. It's actually NIO. So it's in the it uses the same things. It's the same flavor as your server. But in between them, we have the old school API. We have the async REST template API. And this is the thing when the blocking starts. But we don't want to discard it because we love abstractions. We as programmers, we really love abstractions. We're just piling abstractions one on top of another. So it's really hard to take a step back and start using the primitives. And the primitives like async Apache client, just directly. So we don't want to do this. We want our abstractions. And so we have super fast servers, but we have the blocking APIs. And this is where reactive applications are going to come in. So we're going to have the super fast, and nothing in between. Well, maybe a couple threads, but not much more. But, so at this point now, we could write this kind of super fast applications. But we don't do this because it's really cumbersome. And we're waiting for the right APIs to arrive. And Spring 5 has all those APIs. Well, we could do this with reactive or RX before, but it's not so popular. So we're waiting for this Spring things to come out. So okay, having a super fast system, there is no blocking at no point. GC is not an issue. Still, my clients can connect. So this is an example of things that I want to show this example to you because there are a lot of. We tend to concentrate as developers on developing, but we forget about all the other stuff that's there in the world. So what can go wrong? We spend so much time polishing the code. We've used Spring 5 and it's all working. Well, don't be this guy. He deployed the production, forgot about the infrastructure. Don't be this guy ever. Because you can forget about the infrastructure, but the infrastructure won't forget about you. So it's going to come back and bite you whenever you're least expecting it. So all the resources are finite. You might not even know some of the resources exist, but still they are finite, and you cannot, just stretch them. So one of the example of those resources are actually connections and what's underneath. So let's say we have connections coming into our super fast NIO application. And there's one connection, and second, and next one, and the next one, and the next one. And then there's a lot of them, because we have a lot of clients. So this is not unusual. Let's say in the distributed world, there are a lot of people trying to connect with us, and probably most of them have some kind of a connection pool size set to 10 or 20 connections per instance. And then we have 20, 30, 40 clients. So we have hundreds or even thousands of connections coming into our server. And you know what? When you just take an Ubuntu image and deploy it in production, put your service on it, you're just going to have room for around 1,000 connections. Nothing more. Why? Because the way at least the Undertow and Tomcat work, each incoming connection is going to be transferred, is going to be accepted, and thus transformed into a socket, a file descriptor. And we have only 1,000 of them by default, meaning we have way less than 1,000 connections that we can operate on because there are other things that are actually eating up this resource. The outbound connections, the open files, etc. So so this is one of the things that we might not ever think about, but it's still there. There is still a thing that we have to consider. And it can be set by process, of course, but usually we get to know these things when it's too late. So when we had some kind of an outage. And this is me speaking from my experience. So when we first deployed one of our services, we actually got killed because of too many connections. Our clients couldn't connect. And this gives us a nice potential for a DDoS attack. So this is a thing I didn't know was possible until recently. Although when you think about it, it's obvious. So there is a finite resource, you can DDoS it. So what happens when a new connection comes in? So whenever a connection comes in Undertow, it gets accepted. Calling the accept means we're allocating a resource, this file descriptor. Well, there's something happening with it later on. So what if we have a lot of connections coming in the same time? What's going to happen is that while our server can have resources, it can still be unresponsive from the outside. Because there's so much connections coming every second to us that while we could be able to actually process the data, that the response time for our application is really small, even the 99th percentile, we are still in a unresponsive mode. So is it impossible? Of course, it's not impossible. We had this kind of an outage. So if one day you had a problem going to Allegro, it might have been because of this. This is the graph which shows how much connections were created each second to one of our core services. And at some point, something got wrong. And you can see around noon that we started getting insane amounts of connections every second. Imagine creating 20,000 connections per second. I mean, it's an insane number. So even if we remembered about changing the system defaults to 65,000 sockets, which we can open at any time, those resources are disappearing in no time. So our application was still working fine, but all the servers were unresponsive. And this is the moment when the infrastructure reminds about itself. So can it be done better? Well, of course it can, but this is not how the way operates by default. So there's the other way the Undertow can run. And while in the default mode, whenever connection comes, it gets accepted, in the other mode, it actually will not accept it. It will not open the file descriptor. The connection will still be there, but without accepting it, it will not open the file descriptor. But this is something they dropped. Like it used to be the default. It's not anymore because the model with accept suits the Java applications much better. But in the corner cases, it's important to know that we have options. So the things that I would like you all to remember is that, first of all, our apps are just moving JSONs around. So this is a thing we might not be so fond of, but from the technical perspective, this is what we do. Of course, we generate the revenue while moving them around, but it's still just JSONs. Any type of blocking is actually wasting resources. So we have 4 threads in our 4 or 8, not threads, but cores in our machines, usually, unless you're using some very huge physical machines. But anyway, you have 4 or 8 cores, and we should use them wisely. Like, we should not just spawn a lot of threads which are wasting the time of those processors. We're wasting our time on context switching. So we're wasting our memory because each thread is 1 or 2 megs of memory for all the things that are needed. So blocking is wasting resources, and in ideal world, and this is the thing that a lot of languages have been doing already. Like, if you take Erlang, for example, like they have like 4 threads. You have 4 CPUs here. Take those 4 threads and just spin them around, like use them. But you're using the threads constantly. You're not blocking and waiting and wasting resources. And the less we have threads, And so we can also minimize the need for the anti-corruption layer for all those threads which are just blocking waiting by using the non-blocking I/O operations. So it's going to be really easy in Spring 5, but even now you can do it. You just have to get rid of all the abstractions which are actually blurring our vision. They're actually taking away the power from us. All the resources are finite, even if you don't know about it. So there's a lot of things there that are finite. There are a lot of queues in the system itself, in the kernel. We don't have to think about, thankfully. But someday they might come and bite us. So always be nice to your ops team because they know about those things we don't know. And this is the most important thing. Threads, pools, and queues are everywhere. So if you want to monitor if your server is behaving properly or not, the one single point of contact for you, the one single point which you should monitor or start with monitoring is the size of utilization of your thread pool of this anti-corruption layer, how utilized it actually is, and the size of the queue in front of it. Because that's the way you can know, well, if things are going well, if things are going bad, if the utilization is really high, like 90% or above. And you know if you've chosen the right number. Because if any of you actually recently configured HTTP server, what number did you put in when you were asked to choose the thread pool size? Did you measure it carefully? Did you think about it for a while? Did you, I don't know, consult it with colleagues? Or did you just took the value from the previous project or just thought, 300 is enough? So this is just a guess. But and it's fine to take an initial guess, but all the guesses should come up with the numbers afterwards. So measure it, and then you know if this 300 is just waiting resources or if it's really needed. And where is the bottleneck? Oh, yeah, so that would be all from me. Thank you all for listening. If you would like to work with me or would like to contact me, these are the details, and I'm happy to take any questions you might have now.